Okay, folks, I've been asked to have a look at a couple of questions from exercise 12b. So the first question I'm going to run through is question 16. Question 16 says the motion of a particle is described by the vector equation r of t equals 1 minus 2 cos 2t I plus 3 minus 5 sine 2t j for t greater than 0. And the first step here is we're going to find the Cartesian equation. So I'm going to recognise this as my x value and this is my y value, and I've got a trig function here, so I'm going to say that x equals 1 minus 2 cos 2t, and if t is greater than or equal to 0, a quick think about this graph, we've got 1 minus 2 cos, so the whole thing's moved up one place, and then from there it's negative 2 cos 2t, so it's going to go down to negative 1 and up to 3. So up to 3, down to negative 1. So that gives me the domain of my Cartesian equation. So the domain, my x values, will be between negative 1 and positive 3. Okay, my y value, let's have a look at my y value now. So y is equal to 3 minus 5 sine 2t. Okay, again, when t is greater than or equal to 0, a quick sketch of a sine graph. It's a negative sine graph and it's moved up 3 places, and it's going to go down 5 spots and up 5 spots from there. So it's going to take me up to 8 and down to negative 2. So my range of my Cartesian equation will be from negative 2 to 8. Okay, so let's actually work out what this Cartesian equation is. And because this uses trig functions, the trick here is I'm going to rearrange this, and I'm going to make it x minus 1 equals negative 2 cos 2t. I'm going to divide both sides by 2. So it's x minus 1 divided by 2 equals negative cos 2t. And then I'm going to square both sides. And when I square a negative, it becomes positive. So there is my expression for cos squared. Repeat for y, so we'll have y minus 3 is negative 5 sine 2t. Divide by 5, which gives me negative sine 2t, and then square both sides, gives me sine squared 2t. Now it doesn't matter that it's 2t, because my trig identity says that sine theta, or sine squared theta, plus cos squared theta is equal to 1. So it doesn't matter what my angle is, as long as the angle is the same in both sine and cos. And in this case, it is, because we have a 2t and a 2t, or a 2t and a 2t. So all of our angles are 2t, so we can simply substitute into our equation. So using that, we're going to write that y minus 3 on 5 squared plus x minus 1 on 2 squared is equal to 1. So now I have my Cartesian equation. If you want, not necessary, but I would probably rewrite it like this, just because that's how we normally see the expression for a ellipse. And we can see that this is an ellipse because I've got a plus and I've got an equals 1. So I know it's an ellipse. It has moved, my ellipse has moved on the y-axis 3 places to the 3 places up, and it has a major axis of 5, because 5 squared is 25, and on the x-axis it's moved one place to the right, and it has a minor axis of 2. And I just realised I forgot the squared on my expression there. So for part A, find the Cartesian equation of the path. We have done part A at this stage. We've found the Cartesian equation. Part B, find the position at t equals 0, t equals pi on 4, and t equals pi on 2. So if I want to find the position, this is where I need to use my x equation, and at t equals 0, if I substitute in 0 into the x equation, I get 2 cos of 0. Substitute in 0 into the y equation, and I get 3 minus 5 sine of 0. So at this point here, I would have cos of 0 is 1, so 1 minus 2 is 1, and the y value would be 3 minus 0, which is just 3. So this gives me the coordinates x is 1, y is 3. At the point x is, I think the next point was pi on 4. Pi on 4. We'd have 1 minus 2 cos 2 pi on 4. And y of pi on 4 is 3 minus 5 sine of 2 pi on 4. And then this is equal to cos of pi on 2, and cos of pi on 2 is 0, so that gives me the point 1. And sine of pi on 2 is 1, so 3 minus 5, y equals, so that's my x value, y equals negative 2. So I've got a coordinate 1, negative 2. Now we can substitute in the final point, which was pi on 2. I believe, I'll just double check that up the top. Yes, pi on 2. So the x value at pi on 2 is cos of 2 pi on 2. And the y value at pi on 2 is 3 minus 5 sine of 2 pi on 2. And my cos value at pi is negative 1. So this becomes 1 minus 2 times negative 1, which is equal to positive 3. And the y value is 0, so that's y equals 3. Hopefully I've got that correct. So sine of pi is 0, so that becomes 3 again. Okay. Let's now start to work out what is actually going on here in terms of our graph. So this was part B, and I have a feeling that I've made a mistake there, but we'll work that out in a moment. So that's B part 1, B part 2, and B part 3. Alright, and then now let's have a look at C. And C says the time taken by the particle to return to its initial position. So again, this point here, if I want to find out when it returns to its initial position, I can look at my very quick sketch graphs here, and the x value, how long does it take to return to its initial position? Well, that'll be when the period is 2 pi on n, which is equal to 2 pi on 2, because my n value is the value in front of t, which equals pi. So this equation has a period of pi. Now if we look at the period for my sine graph, the period for the sine graph, when does it start repeating itself? It'll be the same thing. So the period of this sine graph is given by 2 pi on 2, which it should start repeating itself at pi, which makes me think that I've done something wrong with my equation over here. So cos of 2 pi on 2 is the same as cos of pi. 1 minus 2 times cos to the minus 1, so that should be equal to positive 3. I don't know, let's work on this. I'm sort of I'm having a bit of trouble at the moment. Brain doesn't want to work. To help me do this, what I'm going to do instead is I'm going to draw a graph. Now, we mentioned before that this is a ellipse, and the ellipse has moved 3 places up on the y-axis, 1, 2, 3, and it's moved 1 place to the right on the x-axis. So I'm going to say that is the center of my ellipse, and then on my x-axis it goes 2 places to the right and 2 places to the left. So if that's 1, that's 1, 2, 1, 2, and then it goes up 3, goes up, how far does it have to go up? 5 places on the y-axis. So if that's 3, 1, 2, 3, 4, 5, roughly keeping my scale, 1, 2, 3, 4, 5. So I get an ellipse, and because my scale on my x and y axes, not happy with that either. That x value should be back 2, which is there, and I get my ellipse something like this. Wow, that's a terrible graph. Where this is the maximum x value at 3 and y value at 3. This is your x value at minus 1 and my x value at y value at 3, and then that would be at 1, 8, and this would be at 1, minus 2. So there's the points on my ellipse, and it's telling me that my coordinates of my starting point was actually a minus 1 up here. Now I'm feeling a little bit better about this. So minus 1, that's where I start from this coordinate. And after pi on 2 seconds, so after pi on 2, we have moved around to this point here. And the midway point, halfway, was at this coordinate here. So what we're finding is that my particle is travelling around the ellipse in this direction, and after t equals pi on 2, I get to this point. So I'm going to need another pi on 2 to get back round to the starting point. So for part C, sort of drawing my graph has helped me work out my error, and I now know that a full revolution will take place after pi seconds. How did I know that? Because at pi on 2 seconds, we have gone halfway around the ellipse. Okay, and then part D, the direction of motion along the curve. Well, from my graph here again, we have a direction of motion where we were going around this way. Okay, so that direction we call anti-clockwise. So part D, travelling anti-clockwise. And that's the end of question 16.